Hi guys. Okay, let's talk about Hess law. First of all, what do we know about enthalpy? Enthalpy is really the heat of a reaction at constant pressure. And the change in enthalpy is independent of the pathways between the initial and the final stages. And the third point we know about enthalpy is that the total enthalpy change for a reaction is the sum of all the changes. Okay, now when we talk about changes, we are really talking about the different pathways or other small reactions. Okay, so for example, when we talk about pathways, what do you mean by pathways? So let us say you want to go from point A to point B. You can go either in one step, or you can go in a series of 3 steps, 1 to 2, 2 to 3, and 3 to 4. So regardless, you are going from point A to point B, but in both the cases, the pathways are different. Another type of pathways to understand is, let us say you are in San Francisco and you want to go to Lake Tahoe. Lake Tahoe is at an elevation of 6,234 feet. San Francisco is at an elevation of 52 feet. So these are independent of the pathways. This is the elevation where it is, that does not change. The elevation remains what it is, irrespective of how you reach to Lake Tahoe. So that is the state function. 52 feet, state function. 6,234 feet, that altitude, state function. But look at the pathways. You can go by driving using a certain freeway, or you can fly by air, right? You can use a train, okay? Or you can use a bus. And if you're a little bit more adventurous, you can even hike and go there, right? Go by walking, it's up to you, right? So all these different pathways, either through flying or through driving or through, driving, or go by train or go by bus, right? Or just, bike, maybe go by bike, So all these different pathways are going to take you from one place to another. But yes, the amount of time or the energy, you can say, is different in each of these pathways. And actually this should be bus and not bass. I'm sorry about that. Okay, now let us look at an example, a real chemical example. And this chemical example here is, we are making nitrogen dioxide. So we are using nitrogen, N2, as a gas, oxygen, 2 moles of oxygen, O2, are combining with the nitrogen, and you're getting 2 moles of nitrogen dioxide. And here, the amount of heat that is involved, and it's a positive, that means this is going to be an endothermic reaction, is 68 kilojoules. So this is one main reaction. Now let's look at some of the pathways or the 2 steps. So the same product can be obtained in 2 steps. So what are those 2 steps? So just give me 1 minute. So the 2 steps are here, nitrogen, N2, as a gas, first reacts with oxygen, 1 mole of oxygen as a gas, and this gives you 2 moles of nitric oxide, and not nitrogen dioxide. It's 2 moles of nitric oxide. And here, so this is the second reaction. Therefore, the enthalpy change, delta H of, let's just put it 2 here, this is going to be 180 kilojoules. So this is the amount of heat that this reaction is going to take, 180. I'm going to just write it down a little bit more cleanly here. Delta H of the second reaction is 180 kilojoules. All right, now look at the third reaction. Now the third reaction here is, which is a part of this, it's going to be in continuation of this. that is, what do we do? Because nitric oxide is not what we need. We want nitrogen dioxide. So what are we going to do? So we're going to take this nitric oxide, which is a gas, and we're going to again blast off oxygen into it. So now it gives us the desired product, which is 2 moles of nitrogen dioxide. And here this is 2 moles. So 2 moles of nitric oxide reacting with oxygen give you 2 moles of nitrogen dioxide. And here the value of the energy, the enthalpy in this case is negative 112 kilojoules. So that is an exothermic reaction. Now you add these two. Add these two, and what do you get here? Okay, now add these two. Now here's something important. You see this 2 nitric oxide here, and you see these 2 nitric oxide here, they cancel out in Hess law. And I'm going to walk you through the principles of, some of the rules of balancing the equations based on the Hess law. So for now, we canceled out the 2 nitric oxide. So what are we left with? We are left with nitrogen, just copy it as it is, plus oxygen, O2, and that gives you now 2 oxygens basically, 2, and then this is going to give you 2 moles of nitrogen dioxide. And here, this is going to be, this is a positive number and this is a negative number. So suddenly we see that delta H2 minus delta H3. Okay, so in other words, 180 kilojoules minus 112 kilojoules. Okay, and this is going to give you 68 kilojoules. So you see, when you combine, so this is a law of summation. When you combine, when you're basically adding these two, and this just happens to be that, this guy is positive and this is negative. So yeah, you have to minus it. Okay, but if you notice it, that this 68 is same as this 68. So in other words, what we have here is that the energy that you get from reaction 1 is equal to the energy from reaction 2 plus the energy or the heat of reaction 3. Okay, and this all of it is 68 kilojoules. So either you can go directly or you can go through these 2-step process, and there are more steps also. So let us now look at the characteristics of Hess law. Okay, and I want you to make a note of this somewhere, so you know that's what you will be needing when you're going to be doing these practicing. Okay, now, or homework. Okay, let me just open my window. All right, so if a reaction is reversed, the change in heat is reversed. What does this mean? Let's look at this. So here, if you have a reaction, let us say xenon, okay, and let me make this a little bit thin. Okay, so here you have xenon as a gas, and this xenon is reacting with 2 moles of fluorine, and that is a gas, and this gives you XeF4, and that is a solid. So you know, xenon tetrafluoride, and here the energy of this reaction is negative 251 kilojoules. All right, so if you were to flip it, then in that case the product becomes the reactant. Xenon tetrafluoride as a solid is now decomposing to give you xenon as a gas and 2 moles of fluorine as a gas. And what happens to the sign of delta H? Now this becomes positive, 251 kilojoules. Clear? Simple. So just make sure that you reverse the signs, but when you're flipping the reaction. And why would you flip the reaction? We will see. It's all a part of balancing. Okay, next is if coefficients in a balanced reaction are multiplied by an integer, then the delta H is also multiplied by the same integer. Now, what does this mean? So let us say we have the same reaction here, which is xenon as a form of a gas, and this is reacting with fluorine, F2 as a gas, and this is going to give you, let us say in this case, xenon difluoride, okay, and this is a solid. All right, and the amount of energy, yeah, maybe not difluoride. It is, I'm sorry, I have this wrong in my notes. This is tetrafluoride, okay, xenon tetrafluoride as a solid, and the value of delta H is equal to negative 251 kilojoules. Now let us say when you are balancing equations by the Hess law, principles, then you end up having, let me use a green color, having a coefficient of 2. So this also gets multiplied by 2, this also gets multiplied by 2, and 251 also gets multiplied by 2. Therefore, now the value of delta H is negative 502 kilojoules. Okay, so whenever you are multiplying, if you were to multiply and for balancing, just make sure you also multiply the heat. So that's another point. Next is cancel the common reactants and the products on the opposite side. So just like you saw here, I had to cancel this guy, this one, 2 moles of nitric oxide and 2 moles of nitric oxide because they were on the opposite side. This is on the reactant side here. This guy is on the reactant side and this one is on the product side. So that is why they could be canceled. But look at this one now. Add the reactants and products on the same side. So that's what you did here. If you look at it, here you had this oxygen, this was 1. This oxygen is 1. When you add it, it becomes 2 oxygens. Okay, so this is the addition. Okay, one of the things. Now comes balance in fractions first, then multiply by the whole numbers. Now this one can get a little bit tricky, but it's like, okay, you've been balancing the equations, molecular equations, using the full numbers, but now we are going to be balancing fractions. And why? Why do we need a fraction? So look at this here. One example. Here is your hydrogen as a gas, okay? And that is reacting with oxygen as a gas. And here you are producing water, okay? And it's in the vaporized state, but let's just put it as a liquid. All right, now comes the question. How do we balance this? So your normal instinct is going to tell you that balance the oxygen by putting a 2 here in front and then put 2 here. So, that's a normal balancing. But in this case, we don't look at it that way. How do we look? We look at it at a real atomic level. In other words, we need one balancing is. So there is 1 oxygen this side, right? Fine. There are 2 oxygens, 2 hydrogens this side. And there are 2 hydrogens here. So we are okay with the hydrogens. But the oxygens we need to balance. So here we have 1 oxygen and we have another oxygen. So there are 2 oxygens, but we are only interested in 1 oxygen. We don't want the other one. Okay, so we only want 1 oxygen. How do we balance it? That means you only need half of these 2. Okay, so that means if you are going to take half of these 2, then you are only left with 1. So basically, if you put half, how do I show this? 1 minute. So here is if you put half, that means here is your 1 oxygen and this is your another oxygen. And when you say you want only half, that means this is the one that you have and this one is, goes away. So you are only looking at 1 atom of oxygen. Okay, so that's how you get that. So half of O2 means 1 half of 2 atoms of oxygen means 1 oxygen atom. Okay, so basically breaking it up into bonds. Now comes this piece here that you just are going to put half, and that is going to balance the oxygen. So this oxygen, 1 atom of oxygen, and this 1 atom of oxygen balanced. Okay, both of them are balanced, and hydrogens are already balanced. So this is how you balance the problems in the fraction state. Now let's look at another example here. Phosphorus reacting with Cl2, and that is going to give you PCl3. Okay, now pay attention. Here, PCl3, phosphorus and phosphorus is fine. This is 1 phosphorus and this is 1 phosphorus. So we don't care about the phosphorus. We have to balance the chlorines. Now, how do we do that? Here, this chlorine is 3 chlorines. So 1 chlorine, 2nd chlorine, and 3rd chlorine. Okay, and here there are only 2 chlorines, 1 and 2. So first thing first, what are we going to do? First is you are going to first make half of the chlorine. That's the way you're going to bring it first. So break this up and make it half of chlorine. Half of chlorine means half of 2 chlorines means 1 chlorine. But you really want to have 3 chlorines. So now it's easier. How are you going to do this now? You have half of chlorine and you just multiply it by 3. So this becomes 3 by 2, and 3 by 2 chlorines can also be written as 1.5 chlorine. Okay, so if you look at it here, that there are 3 halves. 3 half of Cl2 means there are 3 chlorines in reality. So there are in reality there are 3 chlorines, not 1.5, but there are in reality we are looking at the 3 chlorines because we had half of Cl2. Half of Cl2 gave us 1 chlorine. Half of Cl2 gave us 1 chlorine, and then you multiply that by 3. This is in reality 3 chlorines, and it balances with the chlorines on the reactant side, on the product side. Okay, so this is how you will balance it. Now let us look at the applications of this Hess law in calculating the delta H, the conversion of a graphite to diamond. Okay, and we want to find out what is that value for the delta H. So you are given graphite. This will be given to you. What do we know basically? So we know that when graphite reacts with oxygen, or when graphite is combustion, it gives carbon dioxide, and the amount of heat that is liberated, exothermic reaction, is 394 kilojoules per mole. Similarly, you have diamond. Okay, diamond, when it's combusted in the air, carbon dioxide is released and the amount of heat is negative 396 kilojoules per mole. Okay, now we need to find out graphite and diamond. Now here are a few things you have to understand, that here graphite is on the reactant side and diamond is on the product side. Okay, so this is one thing. This is the product, this is the reactant. So this setting is okay for us because graphite is in the reactant side, and this is what we want. Diamond needs to be put on the product side. So what do? We will have to flip it. Flip it means reverse it, So then in that case, the diamond can be made into in that case, when you flip it, then diamond is going to be the product. Okay, at this point, the diamond is a reactant. So in order to make it a product, we will have to flip it. So let's do this. All right, here we have the diamond. Okay, here we have the, let's write this down first. So C, graphite plus oxygen as a gas gives you carbon dioxide, and the value of delta H is equal to negative 394 kilojoules per mole. Kilojoules per mole. Okay, now flipping. Now we have carbon dioxide, CO2 as a gas. Okay, it's very important, this thing is going to give you carbon as a diamond, okay, plus oxygen as a gas. And the value of delta H in this case is positive 396 kilojoules per mole. Okay, so now we have, yeah, because we flipped it. Remember, when you flip it, so the sign is going to be flipped. Sign also flips. Keep that in mind. Okay, so that is why this becomes positive. And now we are going to add these. All right, so now what do you see here? We see that the carbon dioxide and the carbon dioxide cancel out. Okay, oxygens and the oxygen on the other side gets cancelled out. So what are we left with? Our target equation. This is our target reaction. This is also called our target reaction. In the end, this is what you want. So carbon graphite is giving you carbon diamond. Okay, but what happens to the other piece right here? 394 kilojoules per mole. Okay, plus, actually you add these up, but you know, the sign is negative, obviously. So plus 300 positive 396 kilojoules per mole. Okay, and so when you do this math, you get a value of positive 2 kilojoules per mole. Very interesting finding. So we see that when carbon in the form of graphite can be converted to diamond, and the value of delta H is very little, 2 kilojoules per mole. So now comes the question, why don't we see all the graphite, like our pencils and our graphite, you know, nibs or pen or whatever, you know, things of graphite are being converted to diamond? Why? The heat is, the delta H value is not that much. And yes, it is an endothermic reaction, so you have to give very little heat. It's positive, it's positive 2 kilojoules per mole. So why doesn't the graphite turns to diamond? And the answer lies there is chemical kinetics, or the reaction kinetics. And in a reaction kinetics, we try to figure out that, you know, how can we speed this reaction? What can we do? Can we add catalyst? Can we increase the pressure? Can we increase the temperature? Can we, you know, increase some kind of collisions and so forth, some reaction conditions, all those things. So that falls in the domain of reaction kinetics. So in this case, if you increase the pressure, then yes. So this is how they make these artificial diamonds, okay? So this was the very wonderful applications of Hess law, and we covered the theory, and just make sure that you make a note of the reactions, the postulates or the rules, these rules or the characteristics of the Hess law, so that it's easier for you to balance them. And in my next video, I'm going to be starting off the balancing, you know, several steps. So I hope this was easy, and thank you for watching. Bye-bye.